Hello everyone. Today is Tuesday, March 17, 2026. And I'm your host, Nino, broadcasting from my cozy little radio booth. I'm introducing a trending article from the archives today. The radio has a fun atmosphere today. And I'm just sitting here talking to myself about some fascinating science, imagining all of you out there listening to my voice. Before we begin, I have a silly joke for you. Why did the artificial intelligence refuse to cross the road? Because it could not find the semantic invariance in the chicken. Oh right. No one ever understands my jokes, but I find them hilarious anyway. But let's get into the main topic for today. The title is Semantic Invariance in Agentic. The call is Top Civ RHC in 26A3 13,173 long. It is long, but it is packed with some truly mind-blowing insights. I am going to transcribe this for my YouTube channel later, but you get to hear the raw thoughts right now. I want to explain in detail the primary problem that this paper is trying to solve, because it is something that affects all of us who use artificial intelligence. Large language models are increasingly being used as autonomous reasoning agents, which means they do not just chat with us anymore. They actually make decisions, solve complex scientific problems, and coordinate systems without human help. This is what we call agentic, artificial intelligence. However, if we are going to trust these agents to make important choices, you need to be absolutely sure that their reasoning remains stable. This paper introduces a concept called semantic invariance, which basically means that if you ask an artificial intelligence the exact same question, but phrase it slightly differently, it should give you the exact same logical answer. A physics problem should yield the same solution whether you use fancy academic words or practical everyday business terms. The problem is that standard benchmark evaluations completely fail to measure this. These standard tests evaluate models on fixed and rigid problems, assuming that if a model gets it right once, it truly understands the concept. But mounting evidence shows that these models are incredibly fragile. They get confused by superficial changes in an input, even if the actual meaning in the question has not changed at all. If you add a little bit of relevant context, it changes the order of the facts. The artificial intelligence might suddenly give you a completely wrong answer. This fragility undermines the reliability of these agents in the real world. Your human language is messy and unpredictable. To fix this massive blind spot, the researchers presented a metamorphic testing framework. Metamorphic testing is a super cool concept originally made for software systems. Instead of needing a perfect answer key for every single variation of a question, metamorphic testing looks at the relationship between the input and the output. If the input means the same thing, the output must mean the same thing. They applied 8 different transformations to the questions. These included keeping it identical as a baseline, reordering the facts presented, expanding the text with extra words, contracting text to make it shorter, framing it in an academic context, framing it in a business context, and adding contrast formulations that introduced distracting alternatives. They tested these transformations across 7 massive foundation models, including models from the Hermes family, the WIN family, the DeepSeek family, and the Dados family. They use an IT multi-step reasoning problems across 8 scientific domains like physics and economics. Now here's where it gets really interesting, and I want to emphasize this heavily. Model scale does not predict robustness. You would think that the bigger the model, the smarter and more stable it is. Alright. But that is actually false. The smaller model called WIN 330b achieved the highest stability, giving invariant responses nearly 80% of the time, while the much larger models exhibited far greater fragility and confusion. This scale robustness inversion is huge news for anyone building real-world systems, because it proves that throwing more parameters at a problem does not make it more reliable. Another huge finding is that all models universally failed when faced with untrusted transformations. When the researchers presented a problem alongside explicit contrasts with alternative scenarios, it universally destabilized every single model family. This suggests the fundamental flaw in how these models pay attention to information, because the moment you introduce a distractor, their reasoning coherence just completely breaks down. when we compare this new metamorphic testing technology with standard accuracy metrics. It is like comparing a three-dimensional scan to a flat photograph. Standard tests just check if the final answer is right, but this framework digs into the recent traces, using semantic similarity metrics to see if the internal logic stays consistent. Now let us talk about how this applies to everyday life, and I will provide 3 specific application examples based on the content of this paper. Think about medical diagnosis systems in hospitals. In the real world, 5 different doctors might describe the exact same patient's symptoms using 5 different sets of vocabulary. One might be very formal, while another might be more conversational. If an artificial intelligence agent is assisting in diagnosing the patient, it must exhibit perfect semantic invariance. If the technology from this paper is applied, hospitals can test and select only the models that are proven to be robust against paraphrase and fact reordering. This ensures that a patient does not get a wrong diagnosis just because a nurse typed the symptoms in a different order, which literally saves lives and makes healthcare artificial intelligence much safer. Second, let us look at financial decision-making in automated trading systems. Financial markets are flooded with news articles, social media posts, and official earnings reports. An artificial intelligence agent analyzing a company might read a formal academic breakdown of market trends, or a highly abbreviated business context summary. Using the metamorphic testing framework discussed in this paper, financial institutions can evaluate whether their trading algorithms will panic and make. By applying these contextual transformations during the testing phase, banks can deploy smaller and more robust models that ignore distracting and contrastive information, protecting millions of dollars in investments from erratic artificial intelligence behavior. Consider autonomous customer service and legal compliance engines. When everyday people contact customer support, they often include irrelevant personal stories, expand their complaints with extra unnecessary details, or contrast their situation with a totally unrelated product. Standard customer service bots often get confused by this verbosity expansion and contrastive framing. By applying the findings from this research, companies can specifically train and select agents that maintain their reasoning coherence regardless of how wordy or messy the customer input is. This means the artificial intelligence will correctly process a refund or identify a legal issue, whether the customer writes a 2-sentence email or sprawling 10-page reel filled with irrelevant tangents. The impact here is massive for consumer trust, because it guarantees that everyone gets fair and consistent treatment regardless of their communication style. I find it absolutely fascinating that the architecture of the model matters more than its sheer size. The Hermes models were very sensitive to contrastive inputs, while the DeepSeek models got confused just by reordering the facts. This tells us that we cannot just blindly trust artificial intelligence. We have to test it denially. Well, so what you're saying to yourself is that we need to be smarter about how we evaluate these agents. And that is exactly what I'm trying to transcribe for my channel today. I hope you all enjoy this deep dive into semantic invariance, and I will catch you in the next broadcast.